Chapter 14. Enculturated Brains and Honorable Hormones. When you read, you are using a culturally constructed network centered in the left ventral occipital temporal region of your brain. This, the brain's letterbox, is a specialized piece of hardware, or perhaps firmware, for reading. If this brain area suffers targeted damage, literate people become suddenly illiterate, but retain their other cognitive and visual abilities. Some with damage to this region, for example, can still understand written numbers and make numerical calculations, but can't read. This general patterning remains true even for readers of written languages that use symbols to represent whole syllables or words, like Chinese or Japanese. Brain imaging experiments show that the letterbox registers the culturally evolved resemblance between read, in all uppercase letters, and read, in all lowercase letters, even though the two sets of markings bear little physical similarity. But, of course, this happens only in readers of English. Thus, the relationship between uppercase R and lowercase r is literally etched in the brain circuitry of English readers. Similarly, Hebrew characters activate the letterbox in Hebrew readers, but not in monoliterate English readers. This means that highly literate people have different brains than those who are illiterate because they've trained their brains to read. Learning to read specializes your brain for visually processing whatever writing system you are working on. The better you can read, the more specialized the wiring of your brain is for reading. In American children, the letterbox begins to appear around age 8, but doesn't reach maturity until adolescence, assuming the child continues reading. Not only does learning to read build a letterbox in the visual area, between a region specialized to recognize faces and one focused on objects, but it thickens the corpus callosum, the information highway that connects the left and right sides of the brain. Learning to read also modifies the superior temporal sulcus and the left inferior prefrontal cortex, or Broca's area. Overall, this rewiring endows highly literate people with 1. Longer verbal memories, 2. Broader patterns of activation across the brain to spoken words, and 3. A greater awareness of the various sounds that make up words. That is, high levels of literacy improve some cognitive abilities that bear no direct relationship to reading or writing. However, these enhancements don't come without costs. Skilled readers are probably worse at identifying faces, since jury-rigging the relevant brain areas impinges on the fusiform gyrus, an area that specializes in face recognition. In fact, the well-established neurological asymmetry in face processing, favoring the right side of the brain, may be due to the effects of learning to read, which drives face processing out of the left side and shifts what it can to the right side. I was personally glad to hear this, as I now have an excuse for why I forget faces so often. I've recycled some of my facial recognition neuronal firmware to support my reading addiction. These are biological modifications to our brain, but not genetic modifications. They are the end result of thousands of years of cultural evolution, which figured out how to effectively modify our brains without messing with our genetics. Reading and writing are cultural products that have evolved by jury-rigging aspects of our genetically evolved neurological systems for object recognition, visual memory, and language. As the neuroscientist Stanislaus Dehaene has argued, the brain's letterbox gets wired into a kind of neuronal sweet spot, where it has the tools for fine-grained object recognition and connections to language centers. To see the effects of this, consider three recurrent features of writing systems. First, the specific shapes used to form common characters across alphabetic writing systems, like L, X, O, and T, as well as in many of the characters of non-alphabetic writing scripts, such as Chinese characters like the one for mountain, are rapidly recognized by our visual systems. This is not surprising, since these shapes are also the most frequently occurring in the natural world. Second, the meanings or sounds represented by characters in writing do not depend on the absolute size of the character. After all, the apparent size of objects in the real world depends on their distance from the viewer. Children are never taught that letter size is irrelevant. They automatically know or infer this rule. They are, however, occasionally taught that relative letter size is sometimes important, as in Japanese hiragana. Finally, letters or characters in writing are spaced optimally for speed. If the letters are too far apart, your reading speed plummets. Like the other cultural adaptations we've discussed, the symbols used in writing probably didn't begin with basic characters optimized for our object recognition systems, and no one figured out that, by default, children automatically infer size invariance for letters. In fact, many writing systems began with iconic pictograms, probably because, for example, wavy lines that look a bit like water or wheat are easier to remember than arbitrary symbols. Egyptian hieroglyphs used representations of animals, objects, and tools, some of which eventually came to represent phonemes. Such recurrent patterns emerged as cultural evolution selected elements of writing systems that better fit the architecture of our brains. But of course, many other forces influenced cultural evolution, and there may in fact have been entirely different cultural evolutionary avenues to creating highly readable writing systems, systems that fit our brains in quite different ways. Let's consider the Americas, where writing emerged independently from the Eurasian systems. In the Americas, the use of stylized faces as symbols for concepts, dates, proper names, and syllables emerged early and appears to have increased over time. Among the Maya, for example, stylized faces endured for 6 centuries as a central part of the writing system. This unusual element in writing harnesses our innate proclivities, including dedicated brain regions, for recognizing and remembering faces. It also seems likely that skilled Mayan readers probably got better at recognizing and remembering faces in non-reading contexts, unlike me and rather obsessive English readers. This cognitive bias may be reasserting itself in the cultural evolution of modern writing systems, as I suspect that stylized faces are making a comeback. Reading, then, is a cultural evolutionary product that actually rewires our brains to create a cognitive specialization, an almost magical ability to rapidly turn patterns of shapes into language. Most human societies have not had a writing system, and until the last few hundred years, most people did not know how to read or write. This means that most people in modern societies, those with high reading proficiency, because they have learned to read, have different brains with somewhat different cognitive abilities than most people in most societies across human history. This example underlines a crucial point, which we'll explore. Cultural differences are biological differences, but not genetic differences. Human biology, including our brains, involves much more than genes. Oddly, many people, including scientists and science journalists who should know better, often treat cultural differences as if they were non-biological and non-material, almost otherworldly. This confusion emerges when people think that showing something is in the brain or driven by hormones means it's genetic. This is not the case, and the goal of this chapter is to relieve you of these misconceptions, if you have them. Recent evidence clearly shows how culture can shape biology by altering our brain architecture, molding our bodies, and shifting our hormones. Cultural evolution is a type of biological evolution. It's just not a type of genetic evolution. Before proceeding, let me emphasize a key point. Throughout this book so far, I've been laying out how cultural evolution has shaped genetic evolution over tens or hundreds of thousands of years. Now, I'm making a different point. Growing up in a culturally constructed environment shapes our bodies and brains over development non-genetically. Clearly, these two processes are related and interact, and this is what so much work in the evolutionary and social sciences has not sufficiently taken into account. Cultural evolution has figured out many ways to shape our biology. At the most basic level, cultural learning shapes the reward circuitry in our brains so that we come to like and want different things. These differences are neither superficial nor unimportant, as we discussed with chili peppers in Chapter 7. Cultural learning influences what we want to eat, the characteristics we prefer in sexual partners, and how much something hurts. The evidence we'll discuss shows how cultural learning makes food and drinks, like wine, taste better, and makes electricity hurt less. Further, by shaping both the incentives in our social world and our motivations, culture causes us to train our brains in particular ways. In some societies, this involves learning to read, tracking gender or status differences, or using fractions. In other societies, it involves spotting and identifying animal tracks, seeing clearly underwater, or recognizing individual cows within large herds. As part of this process, cultural evolution sometimes constructs what amount to mental prostheses that augment our brains and cognitive abilities, like the physical and mental abaci that permit children to make mental calculations faster than calculators. Reference Chapter 12. Wine, Men, and Song. Researchers applying evolutionary principles to understand sexual attraction have shown that humans tend to prefer certain attributes in their romantic partners and mates. Nevertheless, selecting a romantic partner or mate, especially a long-term one, is precisely the kind of problem that cultural learning is well suited to help solve, because judging mate quality is difficult, uncertain, and time-intensive. By carefully observing who others are attracted to or are inclined to start a relationship with, learners can save their investments of time and energy and can thus better focus their efforts. To test this possibility, the setup of these experiments is generally pretty similar. You get people to rate single images or videos of a target, say Ted, and then expose them to another image or video of the target receiving some kind of attention from a person of the opposite sex, the model, say Stefania. Depending on the cues, participants will often then rate Ted as more attractive and reveal more interest in a long-term relationship with Ted. As expected from Chapter 4, the attraction-enhancing effects emerge or become more pronounced when the model herself, Stefania, is 1. More attractive, 2. Older or more experienced than the participant, and 3. Smiling at Ted, as opposed to having a neutral expression. The effect on people's desire for specific individuals seems clear, but some work also suggests that learners generalize from preferences for specific individuals to traits. So, for example, If Ted dresses in all black and is preferred by Stefania, then a learner may later rate all those who dress in black as more attractive, not just Ted. Empirically, these results have been shown for traits related to dress and hair, and even to a person's eye spacing. By adding brain scanning technology to these kinds of experimental setups, neuroscientists have examined the process by which people change their ratings of facial attractiveness in response to cultural learning. In one experiment, male participants rated 180 female faces on a 7-point scale from 1, unattractive, to 7, attractive. After each rating, they were then shown what they believed to be the average rating for that face by other men. In reality, however, on 60 random faces, this rating was generated by the computer to be 2 to 3 points higher or lower than the participants' rating. The rest of the time, the average rating was calculated to be close to the participants' own rating. Then, a half an hour later, participants underwent brain scanning while they rated all 180 faces again, though no average scores were provided this time. The questions are, how did seeing others' attractiveness ratings influence their subsequent ratings of the same faces, and what was going on in their brains? As usual, participants raised their attractiveness ratings when they saw higher averages from others, and reduced them when they saw lower ratings. The brain scans revealed that seeing the different ratings of others altered their subjective evaluations of those faces. Combined with data from other similar studies, it appears that shifting to agree with others is internally, neurologically, rewarding, and results in enduring neural modifications that change preferences or valuations. In short, cultural learning changes how people perceive or experience faces based on other people's preferences. These are biological and neurological, but not genetic, changes to what people find attractive. Existing research suggests similar processes probably occur with wine, music, and other tastes. Wine provides a great case example. The price of a wine, or anything else, represents an aggregate of many other people's judgments. Consequently, learners should attend to price in figuring out what to like, as well as to the preferences of prestigious experts. While in a brain scanner, participants tasted 5 wines that were labeled and referenced using prices per bottle, specifically $5, $10, $35, $45, and $90. However, unbeknown to the participants, they actually only tasted 3 different wines. 2 of these 3 were labeled as $5 or $45 and as $10 or $90. As usual, people rated the more expensive wines as better, more pleasurable, even though they were actually exactly the same wine. Here, however, we can have a look at people's brains. By comparing the scans from the same wines at different prices, the results show that people drinking the more expensive wines experienced more activation in their medial orbitofrontal cortex, a region associated with the experience of pleasure or pleasantness for odors, tastes, food and drink, and music. Thus, this work suggests that while price does not affect primary sensory regions of the brain, it changes the valuation of the input from those regions. Sensory input is what it is, but cultural learning affects whether we perceive the same sensory input as better or worse. This is particularly interesting for wine because in thousands of double-blind taste tests with wines ranging from $1.65 to $150, Americans without wine training prefer wines that are actually less expensive. It takes some training to get people's wine preferences to correlate positively with price. In terms of rational gift-giving strategies, this suggests that when giving wine as gifts to Americans without wine training, you should buy cheap wine, remove any price indications, and tell them it's really expensive wine. This will maximize their pleasure and yours, saving money, assuming you are okay with lying to make others happier. Overall, this research makes it clear that people's preferences, or tastes, are strongly influenced by observing and inferring the tastes and preferences of others, and that price is one of the cues people use to set their preferences. These effects represent neurological changes, which alter what people find internally rewarding. It would thus be a big mistake to assume people's preferences are fixed or stable. We evolved genetically to have somewhat programmable preferences, and modifying our preferences via cultural learning is part of how we adapt to different environments. Modifying the hippocampus by driving in London. In 2009, I was heading to a conference in London to speak at one of the Royal Society's celebrations of Charles Darwin's Origin of the Species, 1859. After taking the tube, subway, from Heathrow Airport, I jumped into a taxi. We drove for a mile or so and found ourselves stuck in heavy traffic. The driver turned to me and explained that it would take forever to get where I was going because, while my hotel was not far, there was no easy way to get there from our current location. Instead, he recommended that I hop out of the cab, cross the street, enter a pedestrian alleyway, duck under the overhang, make the next left, turn right into another alley, a bunch more directions I have now forgotten, and my hotel would be on the left. Sure enough, his directions were right on, and I was impressed with his mental map of the city. Little did I realize at the time, but my driver's brain, and especially his hippocampus, had probably been modified and specialized for London. Becoming a London taxi driver requires passing a stringent set of examinations on how to get around within a 6-mile radius of Charing Cross train station. Passing this set of examinations usually takes between 3 and 4 years, as London's downtown is a maze of 25,000-plus complex and irregular streets. Several studies have now focused on London taxi drivers, and all tell the same story. Successfully training to become a taxicab driver increases gray matter in the posterior hippocampus. The hippocampus is the brain structure where humans and other species store spatial information. More years of experience driving a taxi means more gray matter in this part of the hippocampus. This renovation in brain architecture allows cabbies to demonstrate better cognitive skills at remembering London landmarks and judging the distances between landmarks. But although most other cognitive abilities are unaffected, these new abilities are not without costs, as cabbies get a bit worse at remembering complex geometrical figures. Being born into a world governed by social norms and reputational consequences means that individuals have immediate incentives to stay in line, follow the rules, and figure out how to excel in locally valued domains, which might involve golf, accounting, reading, abacus use, blowgun hunting, or the performance of shamanistic rituals. Essentially, social norms create a training regime that every child goes through. Children internalize local standards and engage their minds and bodies according to local norms, equipping themselves with locally valued physical skills and mental tools. Taxi driving is the tip of an iceberg. These kinds of studies, which are still in their infancy, have already shown that learning to juggle, speak German, and play the piano all have specific effects on gray and/or white matter in various parts of the brain. Such results suggest that our brains are specialized for the skills and demands of the worlds we inhabit. However, unlike other animals, cultural learning and cultural evolution supplies us with the incentives, for example, reputational improvements, tools, for example, color terms, books, abaci, maps, and numbers, and motivations for modifying our brains. Recognizing this, the emerging subdiscipline of cultural neuroscience has now begun to show the impact of day-to-day culturally transmitted routines, practices, norms, and goals on our brains. These cultural niches result in different cognitive abilities, perceptual biases, attention allocations, and motivations. Let's consider some work done by Trey Hedden and his colleagues. People from different societies vary in their ability to accurately perceive objects and individuals, both in and out of context. Unlike most other populations, educated Westerners have an inclination for, and are good at, focusing on and isolating objects or individuals and abstracting properties for these, while ignoring background activity or context. Alternatively, expressing this in reverse, Westerners tend not to see objects or individuals in context, attend to relationships and their effects, or automatically consider context. Most other people are good at this. One consequence of this characteristic is that Westerners are relatively better at judging the absolute length of a line, independent of the size of the frame surrounding it. Meanwhile, people who grow up in many East Asian societies, hereafter shortened to East Asians, are better at judging the relative length of a line segment within a frame. That is, they are better at scaling the line to the frame size than Westerners. Because of such results, psychologists say Westerners are less frame-dependent than most other populations, including East Asians. Hedden and his colleagues put both European descent Americans and East Asians living in the United States into a brain scanner, fMRI, while they made judgments about whether a newly presented line segment matched the preceding line segment based on either absolute or relative criterion. Crucially, the tasks were designed to be relatively easy, so that with some mental effort, anyone could do well. If you make the task harder, then the Americans would outperform most others on the absolute task, while getting beaten on the relative task. The ease of the task equalizes performance, which means that any differences in brain activation are not due to different final behaviors or judgments, but only to the mental effort involved and the neurological resources tapped to solve the problem. Comparisons of the brain scans for each group show that European descent Americans had greater activation in brain regions associated with effortful control and attention when doing the relative task, the task Westerners are typically bad at. The activated brain regions were located mostly in the frontal and parietal lobes. Meanwhile, East Asians showed more activation in these same brain areas when doing the absolute task. The upshot is that Americans and East Asians revealed different patterns of brain activation for the identical task. They are neurologically different. Now, one of the main points of this book is the importance of culture-gene coevolution during our species' evolutionary history, which means that seeing differences like this does not immediately imply cultural differences. Very different social structures, sustained for hundreds or thousands of years, could, in principle, have led to genetic differences among populations. Remember our discussion of the potential impact of tonal languages on specific genes. In this case, however, genes play, at most, a tiny role, and I suspect no role. Here, Hedden's team used a questionnaire to assess how acculturated East Asian participants were to life in the United States. The result is a striking negative correlation between acculturation and brain activation patterns. The brains of Asians who felt more acculturated to the United States appeared to find the absolute task, the one Westerners are typically better at, less effortful, and engaged in no more effort than many European descent Americans. Of course, this is not decisive, since genes may be influencing only rates or degrees of acculturation. But when combined with studies of immigrants to the United States and Canada, showing that most differences are wiped out in a few generations at most, these psychological differences are most likely, or at least primarily, the product of cultural evolution. Honorable hormones. You are walking down a narrow alleyway. Ahead, blocking your path, is a large man with a drawer pulled out from a filing cabinet. As you approach, he's forced to slide the drawer back in and step against the filing cabinet to permit you to pass. As you pass behind him, he bumps you with his hip and calls you an asshole as you walk away. What's your reaction? How much would this bother you? Well, the answer probably depends on where you grew up. If you are from what have been called honor cultures, you would likely experience this as a challenge to your manhood, assuming you are male. Both your testosterone and cortisol would spike. Testosterone is a hormone associated with readiness for aggression, and cortisol is associated with stress. Your body would be preparing for a fight. The next person you meet will experience an "I'm not taking any shit" attitude, and a very firm handshake to match. If you are not from an honor culture, you would probably not be much affected by the odd encounter. Your hormones wouldn't spike, and the next person you met wouldn't be put on notice that a new sheriff is in town. The world is full of cultures of honor, societies with complex set of social norms that oblige and motivate men and their kin to defend their properties, wives, and families with violence. The social norms here specify that personal or family insults, property damage or theft, and any endangerment to kin jeopardizes a man's reputation unless he replies with immediate and substantial violence that would seem rather disproportionate to those of us from non-honor societies. Flirting with an honorable man's wife or girlfriend will get you punched in the face. Anything more might get you killed. The cultural evolution of such norms makes good adaptive sense in a world without formal or effective policing institutions, where property such as cows, horses, sheep, and goats can be easily stolen. I didn't make up the asshole guy at the filing cabinet. This famous experiment was conducted at the University of Michigan by the psychologist Dick Nesbitt and Dove Cohen. They didn't have to look far for an exotic honor society either. Many regions of the Deep South in the United States were colonized by Scotch-Irish immigrants from Ulster County, Ireland, as well as Highland Scots, who brought an honor culture with them. Of course, many such immigrants also settled in the northern parts of the United States, but there they were assimilated in a few generations. In the South, the early dominance of Scotch-Irish in the founding populations has permitted a culture of honor to persist, especially in the rugged hills, swamps, and other rural regions. In their classic book, Culture of Honor, Dove and Dick mobilize an immense range of evidence showing how these honor norms and their psychological consequences influence everything from moral judgments and child socialization to gun laws and the spin found in newspaper articles. More recently, the economist Pauline Grosjean has highlighted the importance of this phenomenon and used it to explain why the Deep South still has twice the murder rate of the rest of the United States. The two counties with the highest murder rates are in Texas and Georgia. At the state level, the Carolinas have the highest murder rates. Using the first U.S. Census from 1790, Pauline obtained the number of settlers who were immigrants from Ireland and Scotland for 150 counties. There had been a massive migration of Scotch-Irish and Highland Scots in the 18th century prior to the census. For the Deep South, she then shows that counties that had more Scotch-Irish and Highland Scotch settlers in 1790 now have much higher homicide rates in the 21st century, even after statistically removing the current influences of poverty, race, inequality, etc. This is especially true in more remote counties with rugged terrain, where these immigrants and their descendants could maintain their herding lifestyles and culture of honor far from the formal institutions of the newly formed states. Wait, maybe this is genetic, and maybe those Highland Scots brought some aggression genes with them, which have persisted in rural parts of the Deep South. Though it's good to put all hypotheses on the table, this one seems rather unlikely, since neither high levels of violence nor a culture of honor seems to have persisted back in Scotland, which is loaded with Scots. Scotland has a murder rate more like Massachusetts, about one-third that of America's Deep South. Moreover, in New England, and especially the mid-Atlantic states, where many Highland Scots and Scotch-Irish also settled, there's no relationship between settlers in 1790 and 21st century homicide rates. In these places, settlers intermixed with English, German, French, and Dutch settlers, and lost their culture of honor. Here's my point. A package of social norms, which culturally evolved in a world with weak formal institutions, persisted in certain parts of the United States. These social norms evolved to harness men's hormones in ways that shape their behavior, to foster violence in particular honor contexts, such as those involving threats to family and property. This culturally constructed biological reaction leads to higher rates of certain specific types of violent crimes in the Deep South. It's a biological difference, but not a genetic difference. Chemically inert, but biologically active. Placebos open a window on culture and biology. Most people have heard about placebos in the context of testing new medicines. In a randomized control trial, one randomly assigned group gets the drug under testing, and the other group gets a sugar pill or other inert substance. Both groups are told they will get either the drug or the placebo, sugar pill, based on a coin flip, but they don't know which. The common assumption is that this addresses any response bias, which might cause people to inaccurately report getting better or worse based on their opinions about the drug in question. Since the placebo is chemically inert, it can't actually do anything. Right? Wrong. Decades of research now makes it clear that this is not the case. Depending on a person's beliefs, desires, and prior experiences, taking a placebo or experiencing any sham medical procedure, including fake surgery, can activate biological pathways in the body. Often these pathways are the very same pathways triggered by the active chemicals in popular drugs. Placebos can reduce pain, activate the immune system, mitigate irritable bowel symptoms, improve motor coordination in Parkinson's patients, and ameliorate asthma. However, the action and effectiveness of a placebo often depends entirely on how much faith a patient puts in a particular placebo or medical treatment. The more you believe it will work, the more it may actually work. Not only that, there appears to be a synergistic interaction between the size of the placebo effects and the size of the chemical effects. That is, the more one believes a drug like morphine will reduce pain, measured by using placebo morphine, the more effective real morphine actually is. Some drugs don't work at all if administered without the patient's conscious knowledge. That is, the drug requires some placebo effect to catalyze the chemical effects. Culture enters powerfully here because our beliefs and expectations are either set by our own direct experience, what placebo researchers call conditioning, or by cultural learning. Cultural learning could set the beliefs we bring into the doctor's office, or they could be set by the doctor herself after we enter. Moreover, culture can set up a feedback loop. Suppose we first acquire expectations from our social milieu that a medical treatment is very effective. Then we are treated and get better, in part due to the placebo effect created by those initial expectations. The next time, we bring in both the conditioning from the last treatment, our direct experience of getting better, and again our culturally acquired expectations. This kind of feedback could create either virtuous or vicious cycles, making people more or less likely to get better after a treatment. Because of this phenomenon, different medical treatments have different levels of effectiveness in different countries. For example, placebo treatments for ulcers in Germany are twice as effective as the same treatment is in neighboring Denmark and the Netherlands. Germans got better 59% of the time on this placebo, whereas the others got better only 22% of the time. Meanwhile, although placebos can lower diastolic blood pressure by 3.5 millimeters of mercury, compared to about 11 millimeters of mercury for chemically active drugs, in many places, this does not work in Germany. Germans worry a lot about having low blood pressure, which no one else seems very concerned about, so the placebo effect may be inhibited by this culturally transmitted concern. The biology of placebo processes are best mapped out for pain. Some chemically active pain relievers work by firing up the opioid neurotransmission system in brain regions like the dorsolateral prefrontal cortex, anterior cingulate cortex, and nucleus accumbens. Placebo pain relievers fire up these same systems and activate the same brain regions. This effect suggests that placebos are probably doing the same thing biologically as the chemicals. Thus, they are chemically inert, but biologically active. To say placebo effects are in your head is merely to group them with so many other chemically active treatments. Placebos also help patients with Parkinson's disease. Parkinson's patients suffer from 3 motor symptoms: tremors, muscle rigidity, and slowed movements. When patients believe they are receiving an established and powerful Parkinson's drug and told that they should experience motor improvements, brain scans show that the placebo treatment causes a massive release of dopamine in a part of the brain called the striatum. Patients who experience a large dopamine release report more motor improvements. More broadly, the biological pathways used by a range of placebo treatments include suppressing immune responses, releasing hormones like serotonin and dopamine, altering brain activity in particular regions, conditioning opioid receptors in respiratory centers, and reducing beta-adrenergic activity in the cardiovascular systems. This last effect of placebos parallels that created chemically by the class of drugs known as beta blockers, which are used to treat many heart problems. Here's some food for thought. Survival in the years after a heart attack is increased if a patient follows his doctor's orders and takes his medication. In one study, patients who failed to take at least 80% of their medication were dead 5 years later, 1/4 of the time. Those who managed to take 80% or more of their medication were dead only 15% of the time. That makes sense. Now consider that those who failed to take 80% of the placebos were dead 28% of the time, whereas those who strictly adhered to taking their placebos were dead only 15% of the time. So the chemicals in the drug didn't do anything, but it might appear that they did, since staying on the medication improves survival. Both believing a medicine will work and being able to stick to a treatment regime doubles one's chances of survival after a heart attack, even if the treatment is chemically inert. Of course, other studies show that things like beta blockers actually do work better than placebo beta blockers, but strictly sticking to a placebo still improves people's chances of survival as much as a beta blocker. Self-regulation, which can be improved through religious rituals, can extend your life. It hurts so good. Cultural learning is so powerful that it can both reduce our subjective experience of pain and alter our physiological reactions to pain and the threat of pain. It can even make pain desirable. For example, runners like me enjoy running, but normal people think running is painful and something to be avoided. Similarly, weightlifters love that muscle soreness they get after a good workout. It feels good to be sore. Parents, like me, have probably had the experience of watching their child fall and then look up at them for a reaction. If the parent has a smile or looks unconcerned, the child may just stand up and press on. If the parent flashes a grimace, empathetically feeling the fall, the kid is more likely to burst into tears and need a hug. Some pain is good for us, so we humans have to learn to distinguish the good pain, working out, from the bad pain, stab wounds. Experimental work shows that believing a pain-inducing treatment helps one's muscles, activates our opioid and/or our cannabinoid systems, which suppress the pain and increase our pain tolerance. In contrast, believing the identical treatment is damaging our tissues results in a different biological response, which lowers our pain tolerance. My UBC colleague, the psychologist Ken Craig, has directly tested the relationship between cultural learning and pain. Ken's team first exposed research participants to a series of electric shocks that gradually increased in intensity and thus painfulness. Some participants observed another person, a tough model, experience the same shocks right after them, and some did not. Both the participant and the model had to rate how painful the shock was each time. The tough model, however, was secretly working for the experimenter and always rated the pain about 25% less painful than the participant did. Then, after this, the model left, and the participants received a series of random electric shocks. For this new series of shocks, the participants who had seen the tough model rated them half as painful as those who didn't see the tough model. This is interesting, but I'd worry that the participants were just saying the shocks were less painful so they didn't look wimpy to the experimenter compared to the tough model. That's not it. Ken showed that this was not some subjective effect on reporting. Those who saw the tough model showed 1. Declining measurements of electrodermal skin potential, meaning that their bodies stopped reacting to the threat, 2. Lower and more stable heart rates, and 3. Lower stress ratings. Cultural learning from the tough model changed their physiological reactions to the electric shocks. The effect of observing a tough model and inferring their underlying experience is a more potent inducer of placebo effects than mere verbal suggestions. In fact, it's about as effective as direct conditioning. The biological power of witchcraft and astrology. A nocebo is the opposite of a placebo. It's a treatment in which the patient or victim has an expectation of getting worse in some way. There is much less research on nocebos than placebos, probably due to the ethical issues surrounding making people sicker and the lack of obvious clinical applications. However, the writing is on the wall. Giving people a chemically inert treatment that the receiver believes will make them sick often causes a biological response that actually makes them experience negative biological effects. Pain-inducing nocebos activate cholecystokinin and deactivate dopamine in the brains of victims, while bringing on anxiety via what's called the hypothalamic pituitary adrenal axis, HPA. This effect can not only make induced pain worse, it can make normal tactile stimulation painful while increasing anxiety. Throughout the world today, from Africa to New Guinea and across much of human history, people have believed that the strong emotions of others, as well as the active casting of magical spells, could cause sickness, injury, and death. Such belief systems go under the labels of witchcraft or sorcery. Of particular concern in many places is being envied by others, which is associated with the evil eye from Chile to the Middle East. The reason is often simple. People believe that being envied will negatively affect their health or luck. Because of concerns about envy, people hide their successes and avoid excelling too much or standing out. Of course, given what we now know about nocebos, they were quite sensible to behave this way, given their witchcraft beliefs. If they had excelled, other people would have experienced envy toward them. Accurately perceiving this envy from others while holding witchcraft beliefs could very well provoke biological responses in their bodies, potentially leading to illness and sometimes death in pathogen-rich environments. Witchcraft, then, can actually cause material responses in our bodies if we believe it can. To see the power of cultural beliefs, consider California in the late 20th century. In traditional Chinese medicine and astrology, a person's fate is linked to their year of birth, and each birth year is associated with one of the 5 phases: fire, earth, metal, water, and wood. A person born in a particular year is believed to be more affected by the phase associated with their birth year than other people, and each phase is associated with particular bodily organs or with specific symptoms. Fire, for example, is associated with the heart. Earth is associated with lumps, tumors, and nodules. Thus, a person born in 1908, an Earth year, is believed to be more susceptible to tumors. If people believe these associations, then they may act as nocebos. David Phillips and his colleagues tested this idea by comparing the age at death for Chinese and Euro-Americans in California between 1969 and 1990. The prediction is that the combination of getting a particular disease and being born in a year that is believed to be associated with the relevant symptoms or organs of that condition will result in an earlier death. Chinese Americans with an unfavorable disease birth year combination can be compared against both Chinese Americans with different disease birth year combinations and with white Americans with the same diseases, but who presumably don't put much weight on traditional Chinese astrological beliefs. One chart shows the results for bronchitis, emphysema, and asthma, which are associated with the lungs, and thus with birth years ending in 0 or 1. The height of the bar shows how many months a person with the unfavorable disease birth year combination loses from their life. As expected, Americans of European descent in California are not affected, which is crucial since it eliminates the concern that Chinese astrology might be generally true. Looking at all Chinese Americans, females lose 4 years of life and males lose 5. Since many Chinese Americans may no longer put much stock in traditional Chinese astrology, it's worth looking at those living in the larger Chinese communities in Los Angeles and San Francisco, and those born in China, because these populations are more likely to have retained traditional beliefs. For men, the picture doesn't change much, but the years of life lost by women go as high as 9 years. Similar patterns emerge for cancer and heart attacks. Growing up in the social and technological worlds built by cultural evolution changes our biology in profound ways, even when it has not yet had time to alter our gene frequencies. Unconsciously and automatically, we culturally learn motivations, preferences, and values that change our brains in ways that alter what is neurologically rewarding, what we like, and endow us with our rapid intuitive responses, as we discussed in Chapter 11. This does not mean we can culturally learn to like anything, but it's worth noting we can learn to enjoy certain types of pain, including muscle soreness and the burn of a chili pepper. We also culturally acquire mental models or beliefs about how the world works, which direct our attention and generate our expectations. These explain why numerous medical treatments, which are purely placebo effects, and witchcraft often actually work and cause important biological effects. Cumulative cultural evolution also produces packages of technologies, practices, and social norms that provide us with the mental and physical tools, as well as the reputational incentives, to change our brains in ways that create whole new cognitive abilities or hone existing capacities. I've illustrated these effects in discussing abilities related to counting, colors, the mental abacus, frame dependence, reading, and London cab training, and mentioned many others along the way. Recognizing the cultural nature of our species means both realizing that human populations are likely to be psychologically rather different along numerous dimensions related to institutions, technologies, and practices, and that these psychological differences are ultimately non-genetic, biological differences. Equating genetic explanations with biological explanations and distinguishing these from cultural explanations makes no sense. Over the last 14 chapters, we have explored how natural selection has shaped our psychological capacities for culture, how learning from others across generations produces sophisticated technologies, intricate institutions, complex languages, and vast bodies of knowledge, and how these products of cultural evolution have shaped our bodies, brains, and psychologies, both through development in the short run and by driving our genetic evolution in the long run. Now, in chapters 15 and 16, I will turn to the questions of when this trajectory of culture-driven genetic evolution first launched, and why it was our lineage that took off. In chapter 17, I'll bring all these lines together to tackle a series of big questions about the nature of our species, human cooperation, innovation, and the future.